Hi, I'm Rachel, and today we're going to be talking about the hot wire setup. So, for those of you who haven't seen it, this right here is what we're using to characterize our wind tunnel. And we're going to mount it on the sensor mount here that, if you look below, attaches to the gamma sensor that's on the Griffin rotary stage. We have this connected to the FNT box like we talked about in the calibration video before. And then the hot wire itself is connected to the NI 16-bit DAC, or data acquisition, and the CTA is what we actually have connected to the hot wire and how we calibrate it.
All right, hey guys, Jackie here. So as mentioned previously, we're gonna do the hot wire testing. So that is a NACA 18 airfoil. So the hot wire sensor will go on here. So first thing first, we're gonna make sure the hot wire is aiming perpendicular to the flow. So what we're gonna do, we're gonna use that sensor mount here to measure if there's any left on the NACA 18 sensor mount. Since it's a symmetric airfoil, if there's no left, that means the angle of attack is 0, and then you're aiming right directly to the flow. So we're gonna open our ATI sensor software. So that's the ATI sensor software, and then you connect, and the box will pop up. So first thing you're gonna do is bias. So that's air off. And then when everything's ready, so you still see a little bit bias here. So we go ahead, click couple bias, and now we're just gonna turn on the wind tunnel for very slow speed. Okay. So when the tunnel is on, you can actually see the force on the gamma sensor will change. So you will see the drag and lift. So if the sensor is not mounting very well, like this, you will see there will be force reading on the sensor. So the y-axis is on the side of the flow, so it measures directly the left. So if there's reading on the left like this right now, we need to rotate the mount and the sensor so that there's no left. So let's go ahead and then move it back using the rotary stage. And then when we rotate the rotary stage, you will see that the reading for the y-axis will change. And then when it reaches 2, so gonna do a couple times, so that right now you see the y-axis force is on 0, which means there's no left reading on the wing, so that we know our mounting is directly to the flow. Now let's turn off the tunnel here. So then we're gonna take our hot wire sensor, which is here. So the hot wire sensor is very vulnerable, so it can be break very easily. So if you move this cover down, you will see the hot wire coming out. So there is the hot wire. So whenever you're not using the hot wire measuring the flow velocity or doing an experiment, do not expose the hot wire in the free stream or the air, because it will break very easily. So now let's mount the hot wire on the sensor mount. So you're gonna do it very slowly. You're gonna pop the hot wire in here, and then until there's a tape here to stop it. Now you're gonna move it very slowly to expose the hot wire, and then you're gonna rotate the hot wire so that it's perpendicular to the flow, like this. So when everything is mounting okay, and then we're gonna cover the hot wire since we're not doing a testing so far, so we're gonna cover it. And then we're gonna connect the cable here to the mini CTA, and it will read the data from the hot wire. So we're gonna use MATLAB to reading the data from the DAC, just like what we did in the sensor calibration. So go to the app and go hit on the analog input recorder. So wait a couple seconds, it will pop up. So there will be only one signal coming from the hot wire. Is the voltage of the hot wire. So we can only read one signal. So it's pretty slow. Ta-da! So there we go. So here, so we only have the AI 0 that getting the voltage from the hot wire. So if we go auto scale, we can actually see the vibration from the signal of the hot wire. If there's no vibration from the signal, that means your hot wire broke. So let's go set the while limit. So the voltage will be between 1.3 volt to around 2 volts. So let's go ahead, set everything to the right scale. And then you can see the vibration of the signal. So the second thing is to set the rate of the hot wire. So the maximum rate that the hot wire can go is 10 kilohertz. So we can run it at the 10 kilohertz so that we can pick any small vibration in the velocity, especially for the vortices when we measure the vortices after sphere or lens turbine. And then the duration of the time. So for the shuttering system, as it runs at very low frequency, like 0.5 frequency, you want to at least see 2 wave lengths in your frequency, so it's going to be more than 4 seconds. So we can do 5 seconds of data, or we can do 10 seconds of data, so that we can get enough data that we have. So when we set the duration, say let's go 5 here, and then we name your workspace variable, and then you hit record. So then you can record the data from the MATLAB. Again, your data will be shown in the workspace. So here, so your data will be shown in the workspace in the timetable. So you will get your voltage and then your time. So 2 things you're gonna do for the hot wire. Every time you use a new hot wire, you're gonna calibrate the hot wire. So you're gonna mount the hot wire sensor and then turn on the flow at different velocity using the pitot tube we have here to measure the velocity of the free stream, and then take the data and then change the velocity. So the RPM of the tunnel setting, you can go with 25 RPM for increment, of 50 RPM for increment, to get a good calibration of the sensor. Since the calibration curve for the hot wire is not linear, it's a 4th or 5th order polynomial, so you might want to have as much data as you want. So I would recommend a 25 RPM for increment for the calibration. When you get all the calibration data, then you can measure the free stream velocity for whatever experiment you want to do with the hot wire. So that'll be everything for the hot wire. And again, thanks to Michael and LLC for taking the video here.